let's put this information about the derivative into action. We're going to try and find the derivative of f of x equals x cubed. All right, so we have a function f of x. We're looking for another function, which is the derivative of this function. All right, so this new function that we're trying to find is going to explain to us how x cubed is changing, the rate at which it's changing. Okay, so we go to our formula. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. We're looking to find this limit. Now, we're interested when h is 0, and if we plug in 0 for h, we're going to see that we get 0 in both the numerator and the denominator. So this is one of those limits that produces the indeterminate form that we talked about earlier in the year. So we're going to try and make it so that this limit does not produce that anymore, which means we have to do a lot of algebra, a little bit of calculus to get that done. Okay, so again, our function is x cubed. So we want to plug x plus h into x cubed, wherever we see an x. So what happens? We have the limit as h approaches 0, and we have x plus h cubed minus x cubed over h. Okay, so again, what we've done is we've replaced f of x plus h with x plus h cubed, and f of x with x cubed. Just substitution. Okay. Again, we're still going to get 0 over 0 if we plug in 0 for h. So we have to do some more work. Let's get some algebra going. So we have to simplify this x plus h cubed. So over here on the side, right, we've got x plus h cubed, which we know is x plus h times itself again. Well, let's expand it out. Now we need to multiply our terms, which means we're looking at foiling. Let's FOIL the first two binomials, and then we'll FOIL in the third one. So if we FOIL these first two, we have x squared from first, we have xh from outer, we have xh from inner, and we have h squared from last. And that is being multiplied by x plus h. Okay? First, outer, inner, last. We can see that we have two terms that both have an h. So we can combine them. X squared plus 2xh plus h squared. And we still have that x plus h hanging out front. Okay, let me grab another marker here. So now we need to multiply x squared by both terms, and 2xh to both terms, and then h squared to both terms. So we have 6 products that are now going to happen here. When we do x squared times each of these, x squared times x is x cubed, x squared times h is x squared h. Now we go to the 2xh. 2xh times x is 2x squared h. 2xh times h is 2xh squared. Now we go to h squared. H squared times x is going to be xh squared, and h squared times h is going to be h cubed. So we have 1, 2, 3, 4, 5, 6 products that we just did. Some of these terms are alike, so let's combine them. We can combine x squared h and 2x squared h. So we now have 3x squared h. Same thing, xh squared, 2 of them and 1 more, means we have 3xh squared. And finally, that h cubed is still hanging on at the end. So this right here, this 4-term polynomial, is the expansion of x plus h cubed. So we're going to take this out, we're going to sub it out, and we're going to sub this into our numerator. So we're going back over here. We've got the limit as h approaches 0. We can't forget about that. It's kind of tedious to keep writing it, but ultimately all we're trying to do is find a limit, so we have to write the limit notation. Right? And then that x plus h cubed is going to be replaced by this. So we have x cubed plus 3x squared h plus 3xh squared plus h cubed. That's this part of the numerator. But we still have the second part of the numerator, minus x cubed. And we still have our denominator, all over h. Okay. So where do we go from here? Well, let's look at this numerator. There's a bunch of terms up there. What do your algebra skills tell you that we can do with 2 of these terms? You're right, we can cross out the x cubes. X cubed, the opposite of x cubed, they wipe each other out. Okay. Now, if you noticed, those were the only 2 terms that did not have an h. So if when you're doing these problems out, you are able to cross out all the non-h terms, then you are doing the correct step. All right. If you're left with a non-h term, you probably missed a little algebra somewhere along the lines. Okay. Why should all the non-h terms go away? The only way that we can eliminate this h in the denominator is if there's an h all by itself in the numerator. We have h's everywhere, but we don't have one that's all by itself yet. Okay. We are not allowed to cross this h out with that h. We can't do that because this numerator has three parts to it. Okay. We can only cross out an h if that h is all by itself. So let's get that h all by itself. All three of these terms have an h. Let's factor it out. Okay. So limit as h approaches 0. We're going to factor out a common h from that numerator. So we have 3x squared h divided by h is 3x squared. 3xh squared divided by h is 3xh. And h cubed divided by h is h squared. And again, we still have our h in the denominator. Now we have the isolated h. Now that h will eliminate the 1 in the denominator. We've gotten rid of our problem. Our problem was the 0 over 0. We're no longer going to have that 0 over 0. Okay. What happens when we plug in 0 for h now? Well, there's no h in this term, so we just have 3x squared. 3x times h becomes 3x times 0. And h squared becomes 0 squared. That's 0, that's 0, that's 3x squared, so we are left with just 3x squared. And remember, way back here, we have our derivative. So our derivative, f prime of x, is 3x squared. And now we can use this function and we can find the rate at which x cubed is changing at any point that we want. Rather than doing the instantaneous rate of change over and over and over again, we get the one derivative rule, and now plug in 1, plug in 2, plug in -5, plug in 1,000,000. It doesn't matter what you plug in because we have the general rule here. That's our derivative. And whatever value we plug in, that tells us the rate at which x cubed is changing for that particular value of x.